All right, we're going to start chapter 3. Chapter 3 is all dedicated to graphing linear and nonlinear functions. And in this section, we're going to focus mainly or only on linear functions. Before we get into that, though, let's go over our learning objectives. We have 4 objectives that we're going to go through today. The first one is we're going to identify whether a function is linear or if it's not. We're going to determine the x and y intercepts of a linear function from its graph, from a table, and we're going to do it algebraically. Third, we're going to graph a linear function using the x and the y intercepts. And last, graph a linear function by making a table. Well, first off, what is a linear equation or a linear function? If you look at the word linear, the first 4 letters that make up the word is the word line. So these are going to be equations that if we were to graph them, they would make a straight line, much like the line that you see there on the PowerPoint slide. Well, you may want to know some rules of what makes an equation linear. Well, we can flip that around and say, well, what makes an equation not linear? Well, I've got 3 rules that we can use as kind of a checkpoint to say, does it have this rule? Does it have this? Does it have this? Does it break any of those rules to make it not linear? The first one is going to be if it has exponents. So if you see an equation that has an exponent, doesn't matter how many, it automatically makes it not linear. So an example, y equals 2x to the 3rd power, that 3 as an exponent automatically makes this not linear. If we were to try to graph that, it would curve in some type of fashion, which makes it not a completely straight line. The next rule, if a variable appears in the denominator, remember that a denominator is the bottom of a fraction. So anytime that there is a variable, it doesn't have to be a number, or doesn't need to be a number, it just needs to be a letter of some sort, automatically makes it not linear. So an example, y equals 1 over x. The variable that you see there in the denominator, the x, automatically makes this not linear. Again, this makes the graph curve in some fashion. The third and final rule that we're going to talk about is if there is more than one variable in a term. So example, x minus xy equal to 2. The term that has the xy next to it means that they're multiplying 2 variables together, breaks the rule of it being linear. So again, these are 3 particular examples. It could have one of them, it could have all of them, but as long as it's got one, it automatically makes the equation not linear. If you don't see any of these 3, then it is a linear equation. So let's take a look at some examples. We're going to start with example A, y equals 4 minus 3x. So I go through my checklist. Do I see any exponents? I don't see anything as a superscript up in the upper right-hand corner, so we're good there. Do I have a variable in the denominator? There are no fraction bars, so there's definitely not a variable in the denominator. And the last one, do I have more than one variable in a term? Each term either has one letter or it's a number and a letter, so we are good there. So that will make this equation linear. When I jump over to the next one, example B, 6x minus xy equals 4, I go through my checklist. There are no exponents, so we're good there. I don't have a variable in the bottom of a fraction, so we're good. But where I have multiple variables in a term, the xy, that fails it. So this would be nonlinear because there are multiple variables in a term. Why don't you pause the video, try examples 1A and 1B, and when you have your answers, unpause and see if you've got the correct answer. All right, let's see how you did. 1/3 y equal to negative 1. There are no exponents. I do have a fraction, but it's okay to have 3 in the bottom of the denominator. The y is outside of the fraction bar, so that is okay. And last, I don't have multiple variables in a term, so this would be a linear equation. Example 1b. The first rule, do I have any exponents? As you see, I do have an exponent of a 2, so that automatically fails. So this would be nonlinear because it has an exponent. So there it is. You know the difference between a linear equation and you know the difference from when it is nonlinear. The next thing that we'd like to take a look at is finding x and y intercepts. In order to find them, we need to know what they are. By definition, the x-intercept is the point where a graph crosses the x-axis, and it's labeled as an ordered pair as x, whatever that number is, comma, 0. Finding the x-intercept, if I go over to the graph here, I see that it hits the x-axis at 20, so the x-intercept is going to be the number 20. If I label it as an ordered pair, it would be 20, comma, 0. Turn that around, the y-intercept, the point where the graph crosses the y-axis, this time the vertical axis, will be labeled 0, comma, y. So if I look at the graph, where does it hit the vertical axis? I see that it hits it at 30. So the x-intercept is 30, or as an ordered pair, 0, comma, 30. Now, not every graph will have both an x and a y-intercept. Sometimes they only have one. If you look at this graph here, you see that if I extend that line out, it runs completely parallel to the x-axis, so it will never have a chance to hit the x-axis. So this only has a y-intercept at the number 150. So the intercept would be 0, comma, 150. So just be aware of that sometimes there may only be one intercept. Why don't you go ahead and pause the video and see if you can find the x and the y-intercepts for this particular graph. Okay, starting with the x-intercept, we circled it up at -2, so I have an x-intercept at -2, comma, 0, and the y-intercept where it crossed the y-axis at 4, so I have a y-intercept at 0, comma, 4. And keep in mind, it does matter the order that you put these numbers in, because if you write the number first, you're referring to an x-intercept, and if you write the number second, you're referring as a y-intercept. Okay, now let's put all this together. Maybe you don't have the graph, but I'm going to give you a table. We still need to find the x and the y-intercepts. If I give you a table, the x-intercept, you simply need to look at the table and find a y value of 0, because the number that is paired with it is the x-intercept. So if I look at the table here, I found a y value of 0. It is paired with 14, so that makes my x-intercept 14, comma, 0. If I want to find the y-intercept, I need to look for an x value that is 0. And before finding that, actually, you can plot that dot. So I went ahead and plot the dot at 14, 0. Okay, going back into the table and finding, there's my x value of 0, and it is paired with 10,080. So I have a y-intercept that is 0, comma, 10,080. Now that I have that ordered pair, we can plot it. And then when you go to part B says, let's actually graph this. Draw a line between the two of them, and then you have a physical graph that shows this, explaining the situation that's going on here. Now, the situation that is happening is that we have a swimming pool that we're trying to drain, and it's draining at a rate of 720 gallons per hour. So next thing we need to do is describe these intercepts. So the x-intercept of 14, comma, 0 and the y-intercept of 0, comma, 10,080, they represent something and they mean something. They're not just a group of numbers. If I had to explain it, I'm going to start with the y-intercept, meaning that before they even start draining, the pool contains 10,080 gallons of water. How long did that take? Well, it took 14 hours to drain that pool. That's what the x-intercept represents. Now, the most common type of graphing of intercepts that we're going to use is what we got here. We're going to give you a linear equation, and you need to find the x and the y-intercepts and graph them on a piece of graph paper. Now, how do you do that? The process is this. If you want to find an x-intercept, you need to plug 0 in for y and solve for the x. If you would like to find the y-intercept, you're going to plug 0 in for x and solve for the y. So we're going to start with problem 1. X-intercept, plug 0 in for y. So you can see there with the red 0 that I plugged that in for y, and when you simplify that, the reason why we're doing this is we're trying to cancel out one of the variables so that we can solve for the other. By doing that, you're going to have 2x equal to 16 remaining, and then what you need to do from there is divide both sides by the 2, and simplify, and we have x equals 8. That is my x-intercept. So I go to the x-axis and I put my dot at 8. Now I'm going to come back and find the y-intercept. For the y-intercept, we're going to flip-flop this. So instead of putting it in for y, I'm going to put it in for x. So the red 0 goes in for the x this time. That's going to get rid of the 2, and we'll have 4y equal to 16 left. Divide both sides by 4. And we have a y-intercept at positive 4. Go ahead and put my dot on 4 at the y-axis, and then you can draw a line through it. Now the thing with this is that when you do draw your line, you want to take up as much graph paper as possible because linear equations go on forever. They go on forever left. They go on forever right. So there is what 2x plus 4y equal to 16 would look like on graphs. Going on to the next example. The equation does look shuffled around. It's not as much like number 1, but we still use the same process. If I'm going to find the x-intercept first, I still have to put 0 in wherever the y is at. Now you could solve this in a couple steps, but I want to use the least amount of steps possible. So instead of adding a 5 over to both sides, I'm going to go ahead and add x over to make it positive. And we have an x-intercept at negative 5. Go ahead and plot the dot. And I'm going to come back and find the y-intercept. This time I'm going to plug 0 in wherever the x is at. This one works out real nice because then it's done for me. Now I have y equals negative 5. So I have a y-intercept at negative 5. I plot my dot. Then I can draw my line between the two dots and let the arrows go on forever left and forever right. So pretty simple process as long as you know that whatever intercept that you want to find, plug a 0 in for the other letter. Now sometimes it may be easier, or maybe we struggle with finding the x and the y-intercepts. We need to have a fallback plan, and our fallback plan is going to be making an x-y table. I'd like to use some really simple numbers for this. The easiest numbers that I can think of are 1, 0, and negative 1. By that, I'm going to take each of those numbers and I'm going to plug it in for x separately, use my order of operations to figure out what the y number is that pairs with it. So starting with 1, I plug 1 in for x, go through my order of operations. I'm going to get 4 for y. Go back, repeat that process for 0 and negative 1. When I plug 0 in, we're going to get a 1. For the last one, when I plug negative 1 in, get negative 3 plus 1, so I'm going to get negative 2. That's going to give me 3 different ordered pairs. So I've got 1, 4 that I can plot, I've got 0, 1 that I can plot, and then I've got negative 1, negative 2 that I can plot, and then you can draw the line through the 3 points. So there's your fallback plan if we can't remember how to do the x and the y intercepts. Now, not every graph or table is created equally. The ones that people seem to not like are the ones that involve fractions. But I want to show you a shortcut that you can kind of get through this without not having to deal with so many decimals and fractions. If you see a fraction, look at the bottom of the fraction. You see that denominator number? That number right there is going to tell you what positive number and what negative number to put above and below your 0. Okay, so if I got a 3 there, that's going to tell me to put a 3 and a negative 3 to fill in my table. Now here's why this works out real nice, because when I plug in a 3, 1/3 times 3 cancels out the 3's, and you're just going to have 1 left over. So when you do 1 plus 2, now you have a whole number, and this makes it really easy to plot. 0, always nice because it cancels out the fraction. 0 plus 2, you're going to get 2. And then when we plug in negative 3 times 1/3 will give us a negative 1, and negative 1 plus 2 is a positive 1. So much easier points to plot. This would be a whole lot easier than plugging in 1 and negative 1. So let's plot those 3 dots and draw our line between the 3. So there you have it. That's the equation of 1/3 x plus 2 graphed.